Is that working now, Tom?
Yes, we're live.
At last. It has been, yes, been quite a day. Welcome, everybody. Thank you for coming for our last session before Christmas. Apologies for last week. I was away, and Ollie was due to take the class, but he was unwell, so unfortunately we had to skip a week. So apologies for that, for the last minute notification. It's just that time of year. People get a bit sick, including me. So if I'm not, at my best today, then apologies for that. But this is session 4 of our module on custom types, as I'm sure all of you know. Let's get this out of the way first of all. This is my feedback slide that I show at the start of every session. Come and join us on Slack. Come and talk to us. We like to hear from you. We like to chat to you. Everyone's very friendly. So yeah, just go to that URL that you see on the screen, slack.cpp.al, if you want to join us. It's the CPP LAN Slack. It's not run by us, but we sort of piggyback off it. We've got our own chat room in there, #CPP London Uni. So yeah, join up, come and talk to us. That'd be awesome. And with that out of the way, who remembers our last, this slide usually says last week, but who remembers what we were doing last time around? Oh, structs and stuff. Actually, we sort of weren't talking about structs so much. We had a bit of a recap about member functions, and then we started talking about function overloading. This is, I'll talk a bit more about it in a sec. This is the way that you can have multiple functions with the same name in C++, which is a bit unusual as far as programming languages go. Not a lot of programming languages allow you to do this, but C++ does. So we saw a lot of examples with that last week, and we'll see a couple more again in just a moment. And then we went on to talk about a special case of function overloading, which is operator overloading. And this is the way that you can, for operators like the plus and equals equals and minus and divide and all these other ones, about 30 in all, I think, you can define what these operators mean for your own types, which means that you can use your own types as you do the built-in types, things like ints and floats and chars and bools and all of those things. So again, I'll go over this again briefly in just a second. But what have we got on the menu for this week? Well, as I say, we're going to have a bit of a recap. And then after that, we're going to head back on to talk about structs again. And we're going to talk about class invariants and what I mean by class invariant. And we're going to talk about private data and why you want that and how that works. And then towards the end, we'll have an introduction to constructors, what constructors are, why we need them, what they do. So that's what's on the menu today. We're going to be a little bit rushed, but, apologies. I'm sorry. So way back in the midst of time, a fortnight ago, I set people some homework. Saad isn't here today, apparently, and he's the one who always really likes the homework. But this was, it was a little bit more than the exercises I'd given you to date. So rather than just putting a list of instructions on the screen, it's all on GitHub. So the URL is on the screen now. There were 2 exercises in the README. I asked you to complete exercise 1. It was mostly, or entirely, implementing operator overloads, which is what we had looked at last week. I say solutions are on GitHub. The solutions, in fact, are at this URL. Or you can, if you're on the previous page, there's a little drop down that you can select which branch you'd like to look at. So, as usual, I don't intend going over the solutions now, but they are there on the web, and if you did the homework and you're wondering about it, or you want to look at the solutions and you're not quite sure about why I did something the way I did it, come and talk to me when we have a bit of a break, and I'll be happy to answer questions about that. Okie dokie. Yeah. Okay, because it was a long time ago, let's just have a little look back at what we were talking about a fortnight ago, and that was function overloading. So function overloading is the idea that we can have multiple different functions that have the same name but have different parameter lists. Different in number or different in type. Types of the parameters, that is. So what this allows you to do is to have functions with the same name that have equivalent functionality for different types, or at least that's how it's commonly used. So it's sort of one way of kind of doing polymorphism in C++, if you know what polymorphism is. If you don't worry. But as I say, it's something that's a little bit unusual as far as programming languages go. A lot of languages don't allow you to do this, but C++ is one that does. We're actually allowed to overload member functions and non-member functions. That is, functions that belong to a class and functions that are free, floating, don't belong to anything. Last week we talked about only about non-member functions, but everything that I mentioned applies to member functions as well. So it's perfectly legal for you to have two member functions in a class that have the same name but differing parameter lists. Right, that's absolutely fine. And, for some things, quite a common thing to do. So to show you what I mean by this, here I've got two functions. They're both named print. They both, in this case, return nothing. But their parameter lists differ. Parameter lists are different. The first function takes one parameter of type int, and the second function takes one parameter of type float. So as far as C++ is concerned, these are different functions, distinct functions. They have the same name, but because their parameter lists are different, these are two separate, distinct functions. And what this means is that we can now call print both on floats and on integers. So if we call print and give it an integer, 99 in this case, it's going to choose the first function. It's going to call print for integers. And if we pass a float, like this 1.234f, it's going to select the second one. Does that make sense? So what's happening here is that the compiler says, okay, you want to call a function called print. Well, I've got two options. I've got this one with an int and this one with a float. And you've given me an int. So which one of these two functions is the most appropriate? And of course, in this case, it's the first, in the 99 case, it's the first one that's most appropriate. So the compiler tries its best to, what's the word I'm looking for? The compiler tries its best to match the arguments that you provide, that's these things like 99 and 1.234, to match the argument types to the parameter types of the function. That's the types that are written in the function definition. Now in this case, that matching process was really easy because this thing is an int and this thing is a float, so they match exactly. But actually, they don't have to match exactly. The compiler will try various conversions. So for example, if we call print with a double, well, a double is neither an int or a float. So the compiler is going to look at these two overloads of print and try and decide which one is the best match for a double. Neither of them is an exact match, so it's going to look at which one's the best match. And it's actually going to select the float option because that's a better match for a double than a conversion to an int, although both conversions are valid. So this process of trying to match the argument types to the parameter types, this is called overload resolution. And the more you get into C++, probably the more you'll hear about this mysterious thing called overload resolution. And this process is extraordinarily complicated, even by the standards of C++, which is quite complicated as programming languages go, as you've probably gathered by now. The overload resolution rules are just crazy. And I think there are probably about half a dozen people in the world who actually fully understand it. It's one of those things like general relativity, right? If you think you understand it, you probably don't. But in general, the rules are that complicated because they're designed to do what you want most of the time. In fact, almost all the time. Right? 99% of the time, overload resolution is going to select the function that you wanted to call. So for example, whilst we can convert a double to an int, that conversion is truncating. It loses all of the information about the decimal part of the double. So that's quite a bad conversion. We're throwing away lots of information. Whereas a conversion from a double to float, yes, we lose some precision, but we still have a lot more precision than if we just truncated it to an int. So the overload resolution rules for this case, if we tried calling print with a double, would say, okay, well, I haven't got an exact match. Which of these two is better? Well, a conversion to float is, in some sense, less bad than a conversion to an int. Does that make sense? It can happen in some cases that the rules are such that neither or no overload is particularly preferred to any other. That is, you can have multiple overloads that are considered equally good or perhaps equally bad. Right? And in this case, what will actually happen is that you'll get a compile error. So fortunately, this is a good thing, the compiler is not just going to pick one at random and you don't know which one. It's going to say, okay, this is ambiguous. I don't know which of these you actually intended to call. And what actually happens in modern compilers is that they'll print out which are the ones they considered and sometimes even print out the ones they didn't consider and why they didn't consider them. So in that case, what you can do is you can do the manual conversion in that case so that you get an exact match and you can choose which one you want to call. Yeah.
Just a quick question. Does compiler looking in some kind of a table? If, for example, you have 10 functions of print with different types, so somehow you have to... I read a couple of articles that they mentioned virtual table.
Virtual tables, no, virtual tables are something else. Virtual tables are related to virtual functions, which we'll talk about at some point. But that's to do with overriding functions in derived classes. So overload resolution has nothing to do with virtual tables. As to the actual data structures the compilers use internally, I have no idea. That's beyond my level of knowledge. But yes, in general, overload resolution is going to do what you want. If it can't select exactly one overload as the best one, then you're going to get a compile error. And that's a good thing, because it lets you do the conversion manually so that you get the exact right function that you wanted. Come on. So just a slightly fuller example, our old friend, the shapes again. Going to be seeing more of this circle guy later. We've got a circle and a rectangle. And now we can define a function called getArea. It takes a circle, or const reference to a circle actually, and returns pi times the radius. You remember from school, that's the formula for an area of a circle. So this returns the area of the circle that we pass to this function. And what we can also do is write another function called getArea, and this time we take a const reference to a rectangle. And the formula for the area of your rectangle is just the width times the height, if it's axis aligned, which we assume it is. So now we've got two functions, both of which are called getArea, but have different parameter types. One function takes a const reference to a circle, another takes a const reference to a rectangle. So these two functions don't conflict. Come on. So now we create a circle, give it a radius of 2, and we can call this function getArea, or call a function getArea and pass a circle. And again, as I say, what's going to happen here is the compiler is going to look at this, it's going to go, okay, you want to call a function called getArea, well, I've got two choices. And it's going to look at the type of the argument that you've given. Arguments, if there were multiple ones, but in this case there's only one. And it's going to say, okay, well, can I convert a circle into a rectangle? No, I can't. Okay, so this one's not a candidate at all. Can I match a circle against a circle? Well, actually, yes, I can. That's an exact match. That's perfect. So it's going to reject this overload, and it's going to see that this one is available, and it's going to choose this one. And just for completeness, we can do the same thing the other way around as well. We can create a rectangle, and we can call getArea and pass rect, this rectangle instance we've just created. And now the same thing is going to happen again. The compiler is going to look at both overloads. It's going to try and match the supplied argument type, which in this case is a rectangle. It's going to try and match them against the parameter lists of those two overloads. And it's going to say, all right, the first one, well, I can't convert. I have no way of converting a rectangle into a circle, so there's no way I can possibly call that first function. Right? That's out of consideration. Can I call this second one? Yes, I can. And in fact, that's a perfect match. So that would be preferred to almost any other function that you tried to pass to it. So this first one is going to match the version of getArea taking a circle. The second one's going to match the overload of getArea taking a rectangle. And it's going to do exactly what you want and exactly what you expect, which, as I say, 99% of the time is exactly what happens with these overload resolution rules. And that's a good thing. But just to be aware, just to keep in the back of your mind, occasionally, and this mostly happens when you when templates get involved, which are another complication. But occasionally when templates get involved, you can have surprising overloads called, ones you didn't really expect. But 99% of the time, simple cases like this, exactly what happens is exactly what you want and expect to happen. So that's a very brief run through of what we were talking about a fortnight ago about function overloading. This is writing our own functions with choosing our own names. There is a special case, if you like, of function overloading, which is really the reason I talked about it at all, which is to do with operator overloading. And this is, instead of writing functions where we choose the names, we write functions with some predefined names, with special meanings. It's basically what you're doing. And when we write those functions with these special names, if we implement those functions for our own types, it means we can use the operator syntax on our own types, just like we can with the built-in types. This is called operator overloading. So when we have a built-in type, like an int or a float, we can do the things you'd expect to be able to do with those. If we have an int, if we have two ints, we can add them together. If we have two floats, we can divide one by the other and we get another float. Right? These are the built-in operators, the built into C++, and any practical programming language has these sorts of things built in for number numeric types. Some languages have built-in strings, that sort of thing. And they have these operators defined for them as part of the language. So yes, as I say, the plus and the minus when they appear in your source code, they're examples of operators. And C++ has, most programming languages do, have a wide variety. I think there are, is it 25, 30 or so in C++? There are a lot of them. No. And what we can do is define the meaning of these operators for our own types. And it means that once we've implemented these functions, we can use our own types just in exactly the same way with exactly the same syntax as we do the built-in types, like ints, like floats, like bools, etc. And what's the advantage of this? Well, there are a couple. First of all, it can make our source code just look a lot nicer and a lot easier to understand. If you've got, particularly when it comes to mathematical types, so if you've got something like a mathematical matrix vector type library, linear algebra library, right? Operations like vector addition, like scalar multiplication, etc., they have mathematical definitions, and it means that we can write those in our source code in much the same way that they would appear in your maths textbook. You can do a vector times a scalar, or a vector plus a vector. I mean mathematical vectors here, not standard vector. Unfortunate confusion of names. Perhaps a better example is you could, for example, define matrix multiplication to use the star operator, just like integer multiplication or float multiplication uses a star operator. So first of all, it can make our source code look a lot prettier. The second advantage that comes in, a way down the line when you start doing more advanced stuff, is when you start writing generic functions. Is you can write a function that just generically uses the plus operator, and you don't have to care whether somebody has given you an int, or somebody has given you a matrix, or somebody has given you a vector. As long as it has the plus operator defined, it's going to work. Right? And this is extraordinarily powerful. But it's something that we have to worry about a little way down the line. So the way we do this, and I just mentioned it, is we do this by writing a function with a special name. And that special name is operator something, where something is the symbol for the operator that we want to implement. So for example, you could write a function called operator plus that takes two matrices. If we had a class called matrix and we wanted to define matrix addition, we could write a function called operator plus that took two arguments of type matrix, did all the calculations to work out, the appropriate calculations, and then returned us a new matrix. And then, after we've done that, in our source code, we are able to just say, for example, matrix 1 plus matrix 2, just as you can say int 1 plus int 2. Just a little note, this is particularly for anybody who's into Swift. Swift has this really kind of crazy thing where you can define your own new operators, like a new sequence of symbols to define a new operator. So you could, I don't know, define an exponentiation. Exponentiation? Yeah. Operator, if you wanted to. This is not something that's allowed in C++. You're only allowed to overload the existing ones, the ones that say, that are available. Hello, hello. Hopefully this is working now. Right, where was I before that? Yes, so we got this, this last example as well. We're multiplying a float by a vector. Really just wanted to show you that these operator overloads, you don't have to have the same types for the left-hand side and the right-hand side. You're allowed to define cross-type operations as well. This is an example of that right here. So the last thing I want to say about operator overloading, before we move on to some new stuff, is it's cool. And it's one of those things that when people first discover it, they go mad with it. Because it's awesome. You can define pretty much whatever you like. The compiler, C++, compiler, or the language, places almost no restrictions on what you can do in your operator overloads, right? For example, if you have the equals equals operator, which compares, or at least for built-in types, compares whether they have the same value. Well, you'd hope that's going to return a bool to say yes, they have the same value, or no, they don't. But the language doesn't care. You can implement your own equals equals operator to return whatever you like, or do whatever you like. So we have some imaginary my type, and we're just going to write the equals equals operator to return void. Because we can, because the language doesn't stop us. What are we going to do? Oh, well, let's fire the missiles. Is this a good idea? Yeah, no. No, it is not. No, it is not in any way, shape, or form a good idea. Right? Just because you have the freedom to do something doesn't mean that you should do it. Another example of a questionable use of operator overloading is one you've probably seen many, many times already. This is one of those things that seemed like a good idea in 1983 when operator overloading had just been invented and everyone went, yeah, this is cool. Is this overload of, this is the bit shift operator, by the way, does bit shifting on ints, like low-level manipulation of the underlying bits. And it's overloaded for printing, for streaming out, as you've all done many, many times by now. This is a very, very questionable use of operator overloading that people sort of widely see as a bit of a mistake these days. But fortunately, we're not stuck with it for too much longer. C++ 20 will free us from it, but that's for next year. But I want to just conclude by mentioning the golden rule, or at least my golden rule for operator overloading. Only do it when it makes sense, when there is a natural meaning for that operator for your type. Right? By all means, overload the equals equals operator if there is a meaning to it, if you can compare the values of two things. And for most types, you'll find you can do that. And in fact, the equals equals operator makes sense for most types. However, not all types have an addition operation that makes sense. In fact, very few types will have an addition operation that makes sense. Our vec2 did. That's fine because, mathematically we know what it means to add two vectors. But, if you were, I don't know, writing some, let's take our circle example. Does it make sense? What does it mean to add two circles together? Would you add their radiuses? And all that doesn't really make sense, does it? Like mathematically. You can't add two circles. You can't multiply a circle by a rectangle, right? So use operator overloading, but use it when it makes sense. Do as the ints do is one of these phrases that people who are into C++ use. Right? Don't surprise people is basically what this is trying to say. Everybody understands what the operations are on an int and what they do, because we've been adding and subtracting and dividing and multiplying numbers since we were kids. And so if you are going to use operator overloading, then, as I say, only use it, or use your best judgment, but err on the side of caution and use it really only when it makes sense to do so when it's going to increase the clarity of your code for people who are using the types that you're defining. Is it all working, by the way, now, Tom? All right. That was last week. Well, not even last week, the week before. You're looking a bit bored there, John. You've heard all this before, right? You have, but I put a new twist on it every time, new surprises. Let's go on to talk about something new. And let's forget everything I was just talking about function overloading. Though it will be relevant. There's a reason I talked about it when I did, but unfortunately it's not going to be relevant till next year now. But there's a reason I needed to talk about it before I talk about this. Before I talk about access control. So when we write our own types, even relatively simple value types like our circle, there are often cases where we might have multiple data members. Let's get the rectangle, for example, we've got a couple of data members there. There are situations where not every value of those data members makes sense for our type. Oh, I just said rectangle, but I used circle on the slides. So here we've got our old friend, the circle. Just has one member, data member, this radius. Well, what does it mean if I set the radius to -12? What does it mean for a circle to have a negative radius? I don't know. Right? It's you try calling get area on it and you get like minus pi times 144. Like, what does it mean for something to have a negative area? It's a black hole? I don't know. Right? It doesn't make any sense to have a negative radius, is what I'm trying to say. A radius of 0, you could argue, well, maybe that does have a valid representation, maybe that's just a point. But certainly a negative radius, that's kind of meaningless. That's an error. If you have a negative radius for a circle, that's an error in your program. Right? It doesn't make sense for a circle to have a negative radius. Another way of phrasing this is that we can say that our circle has an invariant, a class invariant, that its radius is always non-negative. That's 0 or positive. This is something that is always true for our class, or we desire to always be true for our class. For every instance, all the time. It's an invariant rule. So how can we enforce this? How can we check for errors and make sure nobody's doing something silly, like setting the radius to -12? Well, the usual canonical way to do it is by writing a member function of our class that sets the radius for you, but does the checking beforehand, checks that the new value you've given is appropriate. And in this case, it would check that the radius you're giving it is not less than 0. And these things are very common in a lot of languages. They're called setters, functions which are used to set a piece of member data. Unfortunately, the way we've written our circle class, even if we add this nice new set radius function that does the error checking for us, there's nothing to stop someone just calling .radius and setting it to whatever they like anyway. The solution, in C++, as it is in many other languages you might be familiar with, Java and C#, for example, is that we can declare, optionally declare members of our structs to be private, so that no one else can access them, no one else can change them under our feet. So here's what I mean by the setter function. A function called setRadius takes a parameter which is the new radius. And we check, is the new radius that you want to set this to, is it less than 0? If so, well, in this example, I'm just printing an error message. Maybe you'd want to throw an exception or something. Multiple ways of handling it. Return false would be another option. But in this case, I'm just printing an error message. Otherwise, so if the new radius is not less than 0, we're going to update our radius member. It's this guy up here. We're going to update that with the new radius because we know it's all right. Is this okay?
It's my first time here.
Oh, is it? Oh, welcome. I'm sorry. I usually ask at the beginning if there's anybody new, but I looked around and I didn't spot any new faces, but clearly I didn't look clearly enough. So apologies. Welcome. Yes, you have joined us like 10 sessions in. So if this is all kind of a bit new, don't worry. Again, I usually say this at the beginning, but I skipped it today because I was trying to go a bit faster. But all of the material for all of our previous sessions is available online. All the slides, everything you're seeing now for the previous sessions, that's all on our GitHub page, so github.com/cpplondonuni. And also the recordings, because we're broadcasting out live on the internet, assuming they can hear me, if the microphone's working again. And all those previous videos are on our YouTube channel, so that's youtube.com/cpplondonuni. For those who are watching online, probably already know it, actually, now I come to think of it, because that's where they'll be. But yes, so everything's available if you want to spend Christmas catching up with us. Yeah. Anyway, on with the show. We have this setRadius function. It does the error checking for us. If the new value is okay, we use it. Otherwise, we reject it and we print an error message. Brilliant. Perfect. Awesome. We now no longer can have a negative radius.
Can you remind the difference between cout and cerr?
Did I? Oh, I used Sierra. So if you use Unix, there are basically two different output streams, and by default they both just appear on your console. But if you use Unix, it's possible to redirect the normal output and the error output to different places. And cout goes to the normal standard output, and the cur goes to the error output channel. So if you're using Unix and you're into like Unix pipes and streaming and bash and all that stuff, you can collect these in different places. And so just kind of good practice, I guess, if you have an error message and you want to print it out, to send it to this error stream rather than the regular output stream. Yeah.
So you don't need to private as a circle.
Wait. It's the entire point. Jump the gun, come on. So we create a circle. We haven't given it an initializer, so it's just going to use the default one there, 0.0. And then we're going to call setRadius with the value 10. It's going to say, is 10 less than 0? No, it's not. So we're going to go to the else branch. It's going to set the radius to 10. Happy days. Everything's good. Oh. Unfortunately, there is absolutely nothing to stop a malicious, or more likely just careless programmer, from setting .radius directly, accessing it like this, and setting it to whatever it likes, like -100. So yes, we have our new set radius function, but it's only any good if people actually use it. How can we force people to use it? Well, we can force people to use set radius by preventing access, direct access, to the radius member. We do that by means of access control, the private keyword. Use the private keyword to prevent unauthorized access. So we do this by writing the word private in the definition of our class, private followed by a colon. And after we write that, everything, all the members' definitions that follow after that are considered private to our type. They are inaccessible to the rest of the world. Again, if you're into Java or C#, this is exactly the same meaning that private has there, but the syntax is very slightly different. Things that we declare as private can only be accessed from within member functions of the same type. It is inaccessible to the rest of the world, to the rest of our program. If anybody tries to access it, tries to access private data, that's going to be a compile time error. The compiler is going to catch that and say, hey, no, 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 no. You can't touch that. You can't touch this. No, that's private. No, no, not allowed. So let's show you what I mean by that. So here we've got a struct circle again with its setter. Exactly the same set function we had before. And now whenever you have a set function, you usually want to have a get function as well. Only makes sense. So get radius is pretty simple. It returns the radius. Note that I've marked this member function as const, meaning we can call this if we have a const circle, because it only reads the value, it doesn't alter the value, it doesn't change the value, it doesn't mutate the circle instance. So we mark this member function as const. This one, of course, can't be const because it is changing the value of the radius. And now here's the new bits. We've got the keyword private followed by a colon. And everything that follows from that is considered private to our type, to our circle type, our circle class. In this case, we've only got one private member, and it's the radius. So now let's do exactly what we did before. Create a circle, call set radius with 10. This is going to work exactly as it did before. We're going to pass 10 into set radius. It's going to check, is it less than 0? No, it's not. Okay, so we're going to update the radius exactly as we did before. No problem. This works. This is fine. Now what if we try to do what we did before and call c.radius equals 10? Well, the compiler's going to look at this and go, hang on. This guy, the radius member of circle, our circle C, that's private. The function main is not allowed to access this. This is going to be a hard compile time error. It's going to say this is private. You're not allowed to touch it. You're not allowed to modify it. If we want to get the value of the radius, well, that's fine. We've got this new getter function we just wrote. We can call c.getRadius, and it's going to, in this case, print 10. So that's all good. That's fine. But if we tried to do this, try to say c.radius, that is to access this member directly. Again, this is going to be a compile time error. Radius is private. Doesn't matter whether we're trying to write to it or read from it, it's private. We can't even look at it. We can't even check its value. Does this make sense to people? We can mark data members as private, and then we can't even look at them. And if we want to allow people to access these things, we can have getter and setter functions that are very common. So common, in fact, some languages have like built-in syntax for this. C# has properties that basically does this for you, so does Swift. C++, we don't have it automatically, but we can write them ourselves. It's not that much code. And what this allows us to do, this is what I'm going to say on the next slide. I'll say it in a second. So we can mark our members as private. There is, as you might expect, a corresponding public access level. And the word public works, well, syntactically the same as private, but has the opposite effect. It says these members are available for the entire world to look at or call. There's also a third access level. It's called protected. Things that are marked protected are accessible only from the same class or from derived classes. We're not really talking about derived classes yet. This is kind of object-oriented programming, that inheritance, virtual functions, all of that stuff. We will talk about that in due time, and we'll talk about what the protected keyword does in more detail. But for now, just if you happen to see it, or just know that there is a third access level as well.
So what would the default be?
I'll tell you in just a moment. We can mix and match public, protected, and private sections in our class definition as much as we like. We can start off with a public section, have a private, have some more public, have some more private, have some protected, have some public, private. You get the idea. We can mix and match these as much as we like. As far as the language is concerned, it doesn't care. Right? There is a convention, however, that is kind of wise to stick to unless you have good reasons not to. That it is most common that if you are writing a class definition, first of all, you have the public section, then you have the protected section, which is often empty. Then you have the private section. And the reason for that is that most people are just going to use your type, right? That's kind of the point. And so they only care about the things that they can access, which is the public section. So they don't want to have to scroll down and try and work out like which bits they're actually allowed to call. Right? So you put the public stuff right up the top, and then people who are looking for what member functions your class has just only have to look at the top of the definition. They don't have to care about what the private stuff is because they can't touch it anyway, so why should they care? And again, protected. Some people might care about that if they're deriving from your classes. So we'll put those next. And the private stuff, well, that's only relevant to people who are implementing this type or modifying the behavior of its member functions, because nobody else can touch it. So we put the private stuff last. So again, C++ doesn't care. You can mix and match these sections as much as you like. The convention is to do it in the order public, private, public, protected, private. Now, I had a question at the front about what's the default. Well, I've mentioned several times now, many times, that there is almost no difference between structs and classes in C++. This is, again, something that's different in a lot of other languages. Structs and classes are different things. In C++, they are the same thing. The main difference is in the defaults. So a struct defaults to public access. If you use the struct keyword to define your type, then by default, everything that you write in there is public. The reason for that is for compatibility with C, because C has no notion of private and protected and what have you. But it does have structs. We want to be compatible with C, so we have the same behavior. Classes, on the other hand, default to private access until we say otherwise, until we use one of these public, protected, or private markers. And this is the main difference, the main interesting difference. Anyway, there's one other little difference between structs and classes. Again, that's just the defaults. But this is pretty much the only difference that you really have to care about so much. As I say, the other difference is about the default inheritance level, but you don't have to worry about inheritance levels now. So really, it's up to you whether you prefer to say struct or class. It's one of these things that's it's basically purely stylistic. Because if you say class and then immediately say public, you've got exactly the same behavior as if you just said struct. And conversely, if you said struct and immediately put the private word, that's exactly the same behavior as if you used class in the first place. So it's one of these things that programmers like. It seems like the less important something is, the more strongly held opinions are about it, right? And this is one of those things that some people have very strong opinions about whether to use class and struct and in which circumstance. Personally, I don't care that much. I use struct for everything because I just said it's good to put the public stuff up front, and by default, everything's public in structs. So that's the reason I say struct all this everywhere. But other people prefer to use class. It doesn't matter. This is the whole point of this slide, is to say to you, it doesn't matter. The defaults are different, but you can override them with a single keyword. To show you what I mean, here's exactly what was on the screen just before. Our struct circle. So structs default to public access. So our set radius and get radius functions are public. They can be called by anyone. This is good. This is what we want. This guy, the radius, is in the private section, so he can't be accessed by anyone except within our own member functions, which is why we're allowed to do this. If we couldn't access it within our own member functions, that would, what would be the point? But I could just as well have written it like this. So there are only two differences between these halves. So on the right-hand side, I'm saying class, and then immediately opening the public section. And as far as the compiler is concerned, these two definitions have absolutely identical meaning. Have I stressed this enough yet? The only difference is in the defaults. And we can immediately override the defaults just by saying public. Okay, so I have an exercise for you to do, because of course I do. Oh, yes.
Is there any mechanism to go around it when you do a unit test on the private data? Or
Yes.
is it like every time I have to have a getter if I only use...
There is a way around it. You can define friends, and a friend of your class is allowed to have access to the private members of your class. But I wasn't going to mention that today. We'll come to it later.
The way to do it is you can expose it through a member function that you have a pre-processor if def around, so you only compile it when you're building your tests. Obviously wouldn't need it in production.
Hash define private public.
Or hash. No, let's not go
Yeah. Okay. So I have a little exercise for you to do. Most people here have been doing this quite a bit, so hopefully you'll be able to get on with this okay. I'll give you a few minutes to have a go at this, and I'll walk around, and as usual, you can stop me or talk to Ollie, who might be able to give you better help. So have a go at this, and we'll reconvene in a few moments.
I'm going to have to make convenient.
Yeah, no problem.
No, but where were the slides for the previous lecture?
Okie dokie. I've walked around a couple of people and seen some good solutions. Yeah. Yes, it's on.
It's just that it makes me a little bit nervous to use those sort of things.
So, do you want me to show you your solution, or do you just want to keep on beavering away at it after, later, tomorrow?
Yeah, we can see the solution.
See the solution? Well, certainly the couple of you who are actually working on it, it seemed like you got there. So this is after you've done all the bits. So we've got a class, turned it into a class, and then in order to make the get first name, etc. functions still accessible, for them still to work, we need to put them in the public section of the class. So because it's a class, things don't default to public, so we have to say public. So using class student, everything that follows from here is public. So we've got a function get first name. This is a const member function because it's just a getter, it just reads, it doesn't write. Read-only function, it's const. This just returns the first name field. We have a corresponding set first name. This takes as an argument the new name that we want to set. And in here, first of all, we check that the size is greater than 0. We could have done not.empty as well. That works exactly the same. Somebody did that. So we check that the size is greater than 0 and that the character in position 0, remember C++ counts from 0, the character in position 0 is uppercase. Those are the conditions that we want to ensure. So if these two things are correct, we update our first name field with the new name we were given. I'm not doing anything if the condition is not met, if we're given an empty string or we're given a string with a lowercase first character, then we just won't update it. In theory, we could write an error message, throw an exception, whatever would be appropriate error handling for our class, for our program. And then we have exactly the same code for get surname and set surname. So again, we're doing exactly the same thing, making sure that the new string we've been given is not empty or that its size is greater than 0, either way around. And checking that the first character, that is the one in position 0, is an uppercase character. And if both of those conditions hold, then we update the surname with this new name we were given. So identical implementations in set first name and set surname. The only difference is which of the fields we're updating. So these are the public members of our student class, because they follow after the public keyword. We then introduce a private section, and in this private section we have our two data members, first name and surname, which I've given default values because I wanted to honour our Lord and Master over there, who's not even paying any attention. But, oh yes, one other thing to mention is that although I haven't shown any examples of it, it is perfectly legal to have member functions that are in the private section. Right?
Do you have to instantiate it, or you can leave it blank without equal statement, or it's a bad practice?
Well, let's think about this for a moment. If I didn't have any default initializers and someone just said student, empty brackets, what values would first name and surname have?
Default values for strings.
Which is empty strings. And what is the condition on our class? That strings that the first name and surname fields are not empty. That's the precondition we have in our class, the invariant we want to maintain. So this is one way we can maintain that invariant, just by, you know, inventing. There's a better way of doing it. And that's with constructors. But anyway, so just to finish the thought, it is perfectly fine to have member functions in the private section of your class. And this means that that member function can only be called by other member functions of your class. Or by your friends. Right. So just because I didn't show any examples doesn't mean it's not allowed. It's perfectly allowed.
I did initialize it with nothing. I didn't give it default value and it didn't break.
No, it didn't break. At least the compiler didn't break, but sort of morally we've broken our own rules, right?
Shouldn't it be a compile error?
It's not a compile error because the C++ you have written is perfectly fine.
All right. So
Right.
I just have first a class with empty strings and then I set them.
That's one way of doing it.
All right. So that's just fine.
But, okay, so the thing about class invariants is when let's say we had a member function that's called getInitials. And that just returns you a string, which is the first character of the first name and the first character of the surname. Right? If our class invariant is that the two name fields are not empty, then this imaginary getInitials function doesn't need to do that check, because it knows that's the rule of our class, that these things should never be empty. If these things are empty, things have gone wrong. So it doesn't need to do that check. It doesn't need to check first name is not empty and surname is not empty, and then I can get their first characters. It can just go ahead and look for the first character and just use them, because it knows the strings are not empty.
Yeah, but it's not like we're gonna use an uninitialized class anyway. So what's the problem with the empty string defaults?
In this situation, this was me trying to show you an example.
All right.
Right. Empty string defaults, in the real world, that's not a problem. But this idea of having rules that for the entire lifetime of your class are true about your data members, that is a real thing. That is something that actually, this was just trying to try and show you an imaginary example of that. But it does raise an interesting point, and the point that I want to go on and talk about for the next 13 minutes, which is we can make data members private so that nobody can just go and change them arbitrarily. We can write setter functions that carefully check any modifications to our class to make sure that we're always maintaining our invariants. But what about building our thing in the first place? About establishing our invariants. And there's actually something a bit deeper than this as well. Well, deeper, no, more immediate, I would say. And you can try this out now if you like. We can use private data to prevent access to the fields of our classes, of our structs. This creates a pretty immediate problem that you may or may not notice, is that the way we have been building our things so far, this is going to break. Because if we have our old friend, the circle type, that I haven't repeated the definition here because you've all seen it a million times now, but we've been constructing it like this. And the way this works is it just directly sets the radius. And now it can't do that because the radius is private. And actually, there was nothing to stop you saying circle C curly braces -12. We weren't establishing our invariant when we were constructing our circle. So even before we had the private thing, this was problematic. So once we've introduced private data, we can no longer use this simple syntax to initialize our type, or we can, not syntax, simple method for constructing our types. And there's rather more of a problem in that if we have a const circle, not only do we have to deal with we can only have the default values, whatever we picked, Tom Brezza or a radius of 0, we can never change that radius, because that's the entire point of declaring a const object, is you can never change it once it has been constructed. Once it's been constructed, you can never change the values of any of its data members. So if we can now only construct a circle with a default value, and we can never change, and for a const instance, we can never change that. That's not very good. So we can no longer say this, because we can no longer directly access the radius member to set it. We can do this, which uses just the default value, 0. But we can never change it, because this is const. This is a problem. This is bad. Fortunately, C++ has a solution. That solution is constructors. What we need to do is, now that we have private data, we need to add a constructor to our circle class. Now, again, if you're familiar with a variety of other languages, Java, C#, Python, Swift, whatever, you're probably going to be familiar with the notion of constructors. And they work broadly the same way in C++ as well. So if you feel like you already know this stuff, you probably do. And hopefully C++ will have no surprises for you. But for those who don't, let's talk about what constructors are. A constructor is a special kind of member function. And it's a special kind of member function that is automatically called by the compiler when it is creating an instance of our class. Okay? It's a function that gets called automatically when we create a new object of our class type. And we can use constructors to establish our invariants, to make sure that these rules that we have about our class are true right from the start. We write constructors within our class definition. We write them in the same way that we write member functions, with exactly the same syntax as member functions, except that the name of the constructor is the same as the name of the class. And secondly, constructors are weird because they have no return type. Other than that, we write them in exactly the same way that we write member functions. Constructors can have arguments, do have parameters, parameter list. They have a function name, which is the same as the class name. They don't have a return type, which makes them look a bit weird, but at least you can kind of spot them in the source code quite easily.
Are they always set to public as well, like in Java?
No, you can have private constructors if you want. But by and large, you would usually make your constructor public because that's what makes sense. Within the body of our constructor, we are allowed to modify our member variables, even if the type, when constructed, will be const. Because as I've been using this very careful formulation, right? We can never change it after it has been constructed. But while we are in the process of constructing it, we can modify the values. It's only once the construction process is finished, then we can never change it. So during the construction process, whilst the constructor is running, that is, we can perfectly happily modify our member variables. They're not fixed until the constructor is finished. Then they're cemented, superglued, set in stone, can't change them. Oh, I thought we were going to get line by line. Let me try that again. Anyone else finding this music drifting in through the window a bit distracting? All right, so we've got our circle class. We open the public section. We're going to make our constructors public because that's what makes sense. So this is how we write a constructor. It's a member function that has the same name as our class and that has no return type. Usually the return type would go first. This is a constructor, so it doesn't have a return type. Same name as the class. And we can have whatever types we like, whatever types make sense in our parameter list. In this case, we're taking one parameter. We've called it initial radius. A constructor is a function, and we can do whatever we can do in functions. So we can happily print something out within the body of a constructor. That's fine. In fact, you can do almost anything within the body of a constructor. So yeah, printing, that's fine. More usefully, we're going to try and make sure that our class invariant, that the radius is greater than or equal to 0, that is satisfied right from the get-go, from when this class was first constructed. So if our initial radius is greater than or equal to 0, we will set our radius field to this value. Otherwise, it's just going to have the default value, which, as you'll see in a second, is 0. The getter and the setter are just as we had them before. Not enough room on the slide. And then we have our private section. We have the radius with the default value of 0. 0 satisfies our preconditions. 0 is greater than or equal to 0. That's fine. If we are given an initial radius, we want to make sure that that also meets our conditions. If it doesn't, we're just going to ignore it and use this default value down here. So now, when we call circle, curly braces 1.0, something rather different happens to what happened before. Before, and I was telling you, well, not telling you fibs, but I wasn't being entirely clear. I said this is the way we construct things in C++. I was slightly simplifying things a bit. Actually, that's like a special case. A special case, if you have a struct, or a class even, that only has public members and has no constructors, well, then you can just directly initialize all of its members, right? That's a special case. It's called aggregate initialization. This, a class that has only public members and no, only public member data and no constructors or destructors or whatever. That's called an aggregate. That has like a special form of initialization where you can just directly access each of the members. As soon as you introduce some private data, you can no longer do this aggregate thing. You've got to start writing constructors. And what happens now is it's going to say, OK, I want to create a circle. And you've given me one argument, a float. And it's going to call this constructor function. And it's going to pass the 1.0 as the initial radius. So this is going to call our constructor function. This is going to print out calling constructor. if we call our getRadius function and print out what the radius is, it's going to print 1, because 1 is greater than or equal to 0, so we're going to use that value. Everything's happy. This is fine. And in this case, second case, C2, I've actually changed two things in one go. First of all, I'm now defining a const circle. And secondly, I'm now using a negative number, one we don't like. So what do you think is going to happen in this case? Just in the 2 minutes we have left.
There's going to be a compile error because it doesn't have anything except for a print and constructor.
So we have one vote for a compile error.
Yeah, and it needs a radius.
Okay.
Values just select -1 and 0.
All right, what is the very first thing that's going to happen? It's going to print out calling constructor, yeah. So if I was going to look at this, going to say, okay, you want to construct a circle. Circle has a constructor that matches the argument list you've given. The argument list you've given consists of a single, or double in this case, but close enough. I can call this constructor, so it's going to run this function, and the very first thing it's going to do is it's going to print out calling constructor. Then it's going to say, okay, you gave me this value, initial radius was -1. Is -1 greater than or equal to 0? No. All right, we're going to skip that. And in this case, then we're just going to use this default value for the radius down here, 0. So if we, after we've constructed it, if we then print the radius, it will indeed print out 0.
This one will print 1.
The first one will print 1, the second one will print 0. Oh, it's a typo, sorry, yes, quite right. Let's try this again. Are you happy now? No, thank you, that's good. Right, so a constructor is a special function that gets called when we are creating a new object. That's its purpose. Right? And actually, the whole reason I wanted to talk to you about function overloading last time, was because one of the things we can do, and it's quite common to do, is actually to have multiple constructors that take different argument lists, different parameter lists. And this is exactly just function overloading. I mean, they're quite special functions. They're constructors. They have this funny thing where they have to have the same name as the class and they don't have a return type, but they are just functions. And we can have multiple functions, there's multiple constructors, as long as they have different parameter lists, in the same way that we can have multiple, usually named functions that have different parameter lists. We can have multiple constructors. And that's a pretty common thing to do, in fact. And in that situation, what would happen is the compiler would look at the arguments you give when you're constructing the type, look at the arguments you give, and it would try and match them to one of the available compilers using these complicated overload resolution rules that I was talking about earlier. That was the entire reason we had this little diversion into function overloading last week, was so I could, or not the entire reason, half the reason, was so I could tell you about having multiple constructors this week. But sadly, we are out of time.
If the mark constructor is explicit, does the compiler give compile error because the default type is double?
No, that's not what explicit does. You will find out what explicit does next year. if you want to, you can extend your little student class by giving it a constructor. If you managed to do the last one, and the couple of you who did it had no problems with the last one, so I'm sure you'll have no problems with this one either. We will talk a lot more about constructors and, in fact, other special member functions in the new year. In particular, destructors. Destructors, which are, and I'm not kidding, the number one best thing about C++. Absolutely the best thing about C++. And we will explore those at length in the new year. But that's it for 2019. How sad. But Merry Christmas, everybody. We'll have a good old sing-song, sing lots of carols. Let's not. No, Merry Christmas. I hope everyone will be able to come and join us for a beverage. But that's it for this year. Thank you very much.